1993. This chip is Intel Pentium. 1993. When you guys were born? 2000? What year? 1999? Okay, so 5 years before, 6 years before you guys were born, right? So that is a Pentium processor from Intel. And if you open the package, then take a picture, and you can see this block diagram. So if you have taken computer architecture class, this the box on the right side, that is a CPU. If you remember, there is an instruction patch. Instruction patch unit, instruction read, right? Instruction read, then instruction decode. You have to interpret the machine code and some execution unit. And Intel is providing some complex instruction because it is based on CISC architecture, complex instruction set architecture, not RISC architecture, but reduced instruction set. So complex instruction support, and it is providing floating point operation in hardware. Floating point. So if you think about floating point, what is floating point? The real number, right? In C, what keyword do you use? Float. Float A, B, and C. We have A is equal to, you are assigning 0.1, B 1.25, then C, you want to do some addition of this floating point number. So real number. So how that can be done inside the computer? What do you think? It looks very simple to human, but it is very complicated to the machine, actually. It is not integer. Right? So we are not using just 32-bit integer format. Right? So it is using, if you remember digital logic design course, it is using IEEE standard 754 format. So if you remember, 32-bit format, the first bit is what? Signed bit. It is positive number, right? Positive 0.1, positive 1.5, right? So signed. You have to rewrite that number with that notation. 1 point some binary number, right? Plus or minus 1 point something, some binary number, 0 and 1, right? Multiplied by 2 to the power of something. That is called the mantissa. This one, sorry, exponent. Exponent, and this one is called mantissa. So exponent goes to that field, 8-bit, and 26-bit is used to describe that mantissa. So computer represents that number with that format, and that is stored in memory. So it is not 0.1 to human, right? 0.1, some weird number, but computer is reading, right? That is stored in memory, right? So that is stored in memory, and this number is also stored in memory with that format, right? So CPU is reading these two, data, and separate the sign bit, exponent bit, and mantissa. Separate these two, 3, then for this arithmetic operation, what do you have to do? This exponent should be equal. Then you can do addition. Right? So very complex operation is happening inside the CPU. Okay? So we are not going to talk in detail, but this one. A floating point unit that is taking care of that floating point arithmetic. So floating point addition, subtraction, multiplication, it is not that simple to the machine. Very complicated operation. So anyway, so the block on the right, that is a CPU. Okay. Then we know, right? We know some component, right? Cache, code cache, instruction cache. So it is holding only machine code instructions, right? And data cache, it is holding only data you want to process with instruction cache, and data cache. And the remaining hardware is TLB, that is short for translation group assigned. That is very special hardware. And that special hardware is designed to support virtual memory. If I draw block diagram focusing on addresses, okay, the CPU is generating address that is called virtual address. Okay. Then translation group assigned buffer, that is translating that into physical address. So main memory is actually accessed with that physical address. So address translation is done inside the CPU. Okay. But you have to understand some background. Why you have to do this translation? And for this translation, what do you have to prepare? Okay. That's what you have to understand. Some background and the page table. Okay. That's what I want to talk. So before that, let me show you a simple program. So take a look at this program. Okay, very super simple. A super simple program. So what do you expect if you execute this program? Anyone? So this program is doing what? Location. Yes. So let me compile the code using GCC. GCC. I want output file to be stored into T2. Okay, T2. T2. Then if I execute T2, then what do you expect? It is printing out what? The location of what? Location of the local variable, right? I. Right? Very simple program, right? So if you have n%, that means the location of this local variable I, integer type local variable, right? So before showing you the program, before showing you the output, let me check out. That is my Linux box. Okay. So let me open up another terminal and show you some machine configuration for my Linux box. Okay. So I need to do SSH to the Linux machine. Right? So to check out the CPU and memory, CPU configuration and memory, you can do this. More process CPU information. Right? So then there is Intel processor, Intel Core i7, 7th generation Intel Core i7 running at 3.6 gigahertz. So Intel machine. That is 32-bit machine or 64-bit machine. Intel Core i7. Hey, what do you think? 64-bit machine, right? 64-bit machine. It's running at 3.6 gigahertz, right? So it is 6 gigahertz. So 64-bit machine. What do you mean by 64-bit machine? What is the meaning of that machine? That machine with what is the definition? 32-bit machine, 64-bit machine. What does that mean? What does that mean? Basic unit of data processing. So inside the CPU, you have important component, right? Register file. The ARM has a register file. Intel has a register file. Right? And also, essential component is arithmetic and logical unit. This guy is doing what? So all arithmetic and logical operation. Right? So we call this data path. This data is traveling through that path. Right? Data path. This path, this path, this path. And the register file is also each register is 64-bit in size. So the Cortex A9, the CPU we are studying, is based on 32-bit architecture. 32-bit. That is why each register is 32-bit in size. R0 32-bit, R1 32-bit, right? Right? And 64-bit machine. 64-bit machine, each register 64-bit, and CPU is reading from register file, supply that data into ALU. So this data path is also 64. Data path, right? Data is traveling through the path, right? So output is also 64-bit as told it to you. So the basic unit of data processing, the basic unit. So each clock cycle, CPU can do one arithmetic operation with two 64-bit data. So basic unit. So that is and all the registers 64-bit, and Intel is using different terminology. It is using instruction pointer IP instead of program counter. ARM is using PC, right? Cortex A9. We have register file R02, R15, and R15 is program counter. Right? That is also 32-bit. So from this program counter, address is generated. This address is coming out from program counter to read instruction for instruction patch, right? And for data, right? If you execute LDR, okay, in ARM, right? R0 and R1, then you are reading from this memory location stored here, right? So probably ALU is doing addition operation. You are supplying R1, then 4 from immediate, right? That is immediate. That is contained in the instruction itself. Right? So CPU is supplying R1 and constant 4. ALU will do addition operation, R1 plus 4. That is a memory location. So it is providing another address for this one is for instruction patch. And there is one for data access, memory access, or data access, memory access stage. Okay. So that is also 32-bit address. Okay. How about that Intel 64-bit architecture? The instruction pointer, in other words, program counter, that is 64-bit. Do you think, or other size? Instruction pointer. What do you think? Everything is based on 64-bit because 64-bit architecture, 32-bit architecture, right? Cortex A9. Okay. Each register 32-bit, data path, program counter 32-bit, that is coming out, right? The address. How about this address? What do you think? Is it 64-bit or some other value? What do you think? 48-bit? How did you know? 48-bit. Yes, 48-bit. So why is that? Why 48-bit? So actually the name is RIP. Okay. So IP, then EIP, and RIP. 32-bit architecture, 64-bit architecture, RIP. Anyway, program counter. The reason is, 64-bit, how big space you create with 64-bit. Here, how big space you are creating with 32-bit. The space you are creating is 2 to the power of 32. Okay. In other words, 4 gigabyte space, huge space, right? From location 0, the last location, 8 Fs, 8 Fs, right? The last location. How about that? 64. Assume that it is 64-bit. 64-bit. Then how big space you are creating? 2 to the power of 64, right? 2 to the power of 64. How do you read that number? if you represent that into using that gigabyte or that unit. Exabyte, right? So 2 to the power of 30, that is gig. 2 to the power of 40, that is what? Tera. 50? Right? Petabyte. Then 60 exabyte, right? So if you do the math, then there is 16 exabyte space. So way too big space, right? Too much space, right? Too big space. That is why Intel, okay, this one is too big. So let's reduce, okay? Reduce this one to 48 bit. Okay? So with 48 bit, then how big space you are creating? 256 terabyte, right? 256 terabyte. That is also huge, right? Terabyte, right? And how big is your main memory in your notebook, on your notebook computer? Desktop computer. How big space? How big memory you are using? 16 gigabyte, but unit is different. Terabyte, right? Terabyte. So this is huge also. But anyway, Intel is providing this 48-bit address. 48-bit address. Then that is CPU. Let me check out my memory. Okay. Have you seen this one? 48-bit virtual. 48-bit virtual. Okay. So that is address actually. 48-bit. This address is called virtual address. 48-bit virtual address. Okay. And it says 39-bit physical address. So main memory is accessed with this 39-bit physical address, not this virtual address. So we will talk about that. So now check out memory size. Total memory. My total memory is how big? 16. Not this, not this. Not this. This one is virtual address, right? So this one is called virtual space. Virtual space. 256 terabyte virtual space, right? And actual main memory. Actual memory installed in my Linux box, that is tiny compared to this virtual space. Only 16, right? Only 16 gigabyte of physical, that is main memory. Okay. So if you count, if you count from location 0, then the last location is given. Let's assume memory is installed in consecutive. Memory is allocated in consecutive. Memory is allocated. So we use a decoder to assign memory, memory area, right? You are creating memory space. Then you are populating actual hardware component, right? So some physical space. You have some physical space. So according to that number, okay, let me. So this one is called virtual space, and we have 39-bit physical address. Physical address. That means it is creating how big space? 39-bit physical space, right? Virtual space and physical space. Physical space. How big? 2 to the power of 39. The space is 512 gigabyte space. So onto that space, you are populating hardware component. So actual main memory and I/O devices. And by main memory only 16, right? 16 gigabyte. Okay, let's assume that is assigned from location 0 to some place. The location 0. What is the last location? 2 to the power of what? 2 to the power of 34. So all 34 bits are 1, and that is the last location. Last location. Okay. So then the one above, the location one above is what? Sorry, 2004, right? 4, 0. This is the location 1 byte above, right? 1 byte above the last location of this memory. Right? 32-bit, 8 zeros. 32-bit. Right? 4 is what? In binary, 1, 0, 0. So 34-bit. So 1 above. Right? So that is the location, right? So with that said, right? So our main memory, my memory is located from location 0 to last location is this. Right? And let me execute that example program, C program. This example program is supposed to print out memory location of this local variable, right? So let me execute C2, then get this. It is a super big number, right? So if you, I don't know how to read, get this, 4, right? So 12 hexadecimal, numbers, right? 12, right? So that is what? That is, it seems like 12 hex number, 12 hex. Then each hex need 4 bit, right? 4 bit. 12 multiplied by 4, that means 48 bit, right? 48 bit address. So if you think about that number, then it is not, it is not within that range, of course, right? So 12, right? But you have only 9 hex, hex numbers, right? So that location is not within your physical memory, right? Somewhere else, right? So what do you think? Is it what? That location is what? Which address? Virtual address? Okay, some location in virtual space. What do you think? Do you agree with that answer? How many of you have watched movie called Matrix? How many of you Matrix? I think that is our best sci-fi movie in my opinion. Do you agree? Who are the main characters? Main characters in the movie? Neo and Trinity and Morpheus, Oracle. Okay. So the story begins with what? Story begins with Neo living in a computer-generated virtual world. Computer-generated virtual world called Matrix, like metaverse, right? These days, right? And then Neo never, know he's living in that virtual world, right? But he always thinks something suspicious is going on in the world, right? And Neo is the best hacker, right? And the Morpheus is the second best. But Morpheus knows the secret, right? Morpheus knows, the Neo is living in, people are living in virtual, computer-generated virtual matrix. So on the rainy day, right, Neo and Morpheus met together, and Morpheus offered 2 choices: red pill or blue pill. You take red pill, what happens? Red pill, then you are waking up from the dream world, right, and see the real world, right? And if you take blue pill, stay in the dream world, right? And live there forever. So Neo's decision is what? Take red pill. Right? He took red pill. He wakes up from the dream world and see what's going on in the real world. And finally, he saved the world. Right? He saved the world. Right? So guys, you haven't lived in a dream world. You know, you are living in a dream world. You know, that is not actual address, virtual address. That is location somewhere in this virtual space. So if you do some math, right? So location 0 and the last location, so all 48 bits are 1, right? So 12 Fs, right? 48, right? 12 hexa digit, right? Then location, and there's location 7FF. To make it simple, location seems like very close to 8000. That location, very close to that location. So right below, somewhere below, 7FF or something, somewhere below here. That is the location, a local variable, right? So I hope that is giving you enough motivation why you have to study, virtual memory and TLB. Okay, so let's talk about real stuff now. So let's talk about virtual memory, right? Virtual memory. This one is from computer architecture class. So why you need virtual memory, right? That is fine. This one. Okay. Yes, please. Okay, so think about multitasking or multi-processing or multi-programming, whatever the name is, that kind of system. You have a bunch of tasks to execute on your computer. You are doing some mini project, right? I ask you to run 3 different tasks, and your job is run mini operating system to execute three different tasks in round robin fashion, time multiplex manner. Similar to that, operating system, you have a bunch of 1,000 different programs to execute 1,000 different programs. And how would you execute that many different programs? Okay. So assuming that, forget about virtual memory, forget about that virtual memory, then simply program counter is connected to main memory. Right? That is only address bus connected to main memory. Then let's assume the operating system is using time multiplex mechanism to execute that many different programs, right? So first 1 millisecond, task number 1 is executed, and second 1 millisecond, task number 2 and task number 3, and then task number 1 again, task 1, task 2, task 3, task 1, So you have only 3 tasks to execute. Then here let's assume you have only 64 KB memory. Right? And let's say task 1 is taking size of binary is how big? Let's say 32 kilobytes. So task 2, let's say the binary size 16 kilobytes. And task 3, the binary size 48 kilobytes. Then let's execute task 1 and 2 and 3 one by one in time multiplex manner. These 3 different tasks are stored in main memory, right? Binary is stored here. Task 1, task 2, task 3. I'm trying to show you if you don't have virtual memory implemented. Is it convenient to? Is it effective and convenient to execute these 3 different tasks like you are doing in the class project? Okay. So let's execute task number 1. Then to execute task number 1, you have to place task 1 to the main memory. Right? So probably you are placing this 32 kilobyte task into here. So location 0. Then task 1 is placed here. Then starting from, you are setting program counter 0. Because your program probably starts from the first location. Okay. So your program starts from here. Then program counter is pointing the location, then start executing that program. So execute this code, then read the second code and execute, read next code and execute. Then 1 millisecond elapsed at this point. Let's say at this point. So location, let's say 1000. So 1 millisecond elapsed. So you have to stop task 1. In other words, you have to switch out. You have to switch out task 1 and switch in, switch out. Okay, you are out. Then I need to switch in task 2. Right? So to execute task 2, what do you have to do? Probably you have some empty area in main memory. So probably your choice is 16 kilobyte. Why don't you place 16 kilobyte here? 16 kilobyte, to here. Then probably code your program starts from that location. So then the actual address 32 and kilobyte to power 15. So power of 15. The location is 3 zeros, right? 8 0 0 0. Start from the second program, task 2. Start from that location. So what you have to do is, okay, so you are operating system design. So you have to set the program counter to 8,000. 8,000. So that means it is pointing that location. CPU read that instruction. Okay. And next instruction is executed. Right? Then 1 millisecond elapsed. Then at this point, probably T2 got executed until that point. Let's say it is location is 9,000. T2 stopped at that location. When you resume task 2, you have to start from the location. You have to resume from the location. Okay? So now it is time to execute task 3. Now what do you want to do? What do you have to do? Task 3 program size, 48 kilobyte. Okay? But the remaining memory is not enough to place that guy into here. Okay, only 60 kilobyte left. So what do you probably have to do? Probably, okay, then let me draw main memory again here. Same main memory. So probably you have to kick out. Okay, so kick out this guy, 48 kilobyte. you need this whole 48 kilobyte space. Okay, you will kick out task 1 binary, task 2 binary from the main memory, then place a task 3, P3. Then set program counter to 0 to point their location. The location of the first instruction in T3. Okay. So CPU executes T3 from the first instruction, then 1 millisecond is elapsed. Okay. Then probably stopped at this location. Let's say it is 2000. Now it is time to re-execute, resume task 1. So what do you have to do? To execute task 1, then you have to place task 1 to main memory. Okay. But this is not enough space. Also, you cannot place that into here because program stopped at location 1000. So you have to place task 1 from the exactly same location, not new location, because program stopped at 1000. Okay. So the point is, every time without virtual memory, I'm talking about without virtual memory, how would you implement this multitasking, multiprocessing system? You have to place this binary to exactly same location every time you place. Okay. Then whole binary, probably this whole binary should be placed in memory, even though you don't execute. This is never executed at the first time. So probably this one is inefficient solution to execute multiple different programs. So computer scientist was thinking about how to execute these multiple programs on a computer system. So solution to this issue is virtual. They are separating physical space. Separating physical space. They are creating virtual space. They created virtual space and separate that from this physical space. You have physical space and virtual space. And your application program is executed on this virtual space. On this virtual space. And this virtual space is at some point in time, this virtual space is used only by your program. It's clean, white. Nobody is using this space but your program, your application T1. Then T1 is executed. You are fully utilizing this virtual space, and the rest is managed by operating system. When you execute task number 2, and task number 2 is also fully utilizing this whole virtual space. Okay? And the rest is managed by OS. The same thing goes to task 3. Task 3 executed, this whole space is occupied, fully utilized by task 3. The thing is, when you compile the binary, it's equal task 1. Compile the binary, and the binary is laid out on this virtual space in mind, from location 0 to this abundant space. Okay. So let me show you some animation. A little bit confusing, right? So let me show you this animation. So here, CPU is generating virtual address, then physical address. Main memory is attached to this physical address. Okay. And hard disk contains everything. Hard disk has Windows, okay, and MS Word program and Hello World program. And each program is logically divided into fixed sized blocks. Okay. Each program is divided into fixed size. We call that page. Page-based split. And then main memory, that is the main memory status at some point in time. So main memory contains pages, yellow pages from these windows, and green pages from MS Word. Then now it is time to execute our hello world. Right? Then CPU is generating location 0. Location 0. Then that that page should be located, should be placed in main memory. So operating system find out. Okay, there are 3 candidates. Okay, these 3 candidates. Nobody using these 3 places. So that block should be replaced at that location. So page number 0 is located actually here. So CPU execute from virtual space, right? 1024 instructions. If the code, there is no branch, right? So here, from this virtual space, right? 4K by page, then there are 1024 instructions, which is each instruction is 4 bytes in size, right? So CPU execute. Okay. CPU execute means CPU simply generate memory location, starting from location 0, right? Then 4, then 8, and C, and so on. Then accessing some memory location, then that page is actually located there in physical memory. Then it is time to execute the code in the next page. Then that page is not placed in main memory. So operating system is making decision. In that page, okay, I need to place that page into that empty location, empty page. So page number 0 here, page number 1 here. So execute it. Then page number 3, 2 is okay. Place it here. So the actual pages in this hello world program are dispersed, distributed in main memory, not located in consecutive memory locations. Then next page. Then main memory is fully occupied by pages from many programs. Now you have to kick out one guy. You have to sacrifice one guy. Right? So OS will make decision. Probably that page is least recently used page. So remove that guy, then place new into the application. So if you take a snapshot of main memory is populated with pages from many different programs. So main memory we can define main virtual memory is using main memory as a cache or hard disk. Hard disk contains everything, and main memory is storing frequently used pages from your program. So it is cache. Main memory is a cache or hard disk. Cache of hard disk. It's still confusing, right? So what happens is when you write program task1.c, right? Task1.c, you compile it, right? Compile the code, and you are getting binary. Then compiler generates this binary. Then this binary was created with virtual space in mind. Okay, you compile this code. Then this binary layout code, right? Your program, right? Your program is composed of code and data. Code and data. That is your program. That is your program. You want to process this data with your code, right? And this layout location 02 somewhere, right? That layout was this layout is created with a virtual space, this virtual space in mind. So nobody is using this virtual space, but your code. You are fully utilizing this virtual space, this abundant virtual space. And when you context switch, right, then T2 is fully utilizing this virtual space. Okay. So your program, that means your program can be as big as, when you think about how big your program can be, can your program be? Your program can be how big? 16 exabyte? No way, right? You cannot, right? So that is limited by this program counter, size of program counter. First limited by the program counter, right? Because that is creating this virtual space. So your program cannot be bigger than this virtual space. There is a limitation. So again, your program is compiled and binary was created with virtual space in mind. This is consecutive space, right? And that binary is stored in hard disk. So your code and data, right? So that binary again was laid out with virtual space in mind. So simply CPU is generated. Of course, it is virtual address. Right? Then CPU is to execute task 1. CPU start fetching instruction from location 0. That means simply generate address 0. Then because it is virtual, there's nothing actually, right? Virtual space, right? Nothing, empty. There's nothing, just wire, address line. So CPU is generating address. Then your code should be fetched from actual main memory, right? But the code can be placed anywhere in this main memory. The first 4K byte can be placed here and there, any place, depending on main memory status. Right? So again, let me split this address into 2. So this is virtual address. Then somehow you have to translate that into physical address, something. Right? So we have TLB, virtual address, location 0. But physical address to access first is, let's say it is addition instruction, first code, and that code is actually placed here. Addition, very high memory location. So physical address, probably you are generating so 64K byte. Then probably F000. There is physical address. Again, CPU is generating location 0, virtual address 0. Then someone should do translation. Generate F0 because that page, the first page is located top, this 4K byte place. The first code is reading from this location and supply to. So try to visualize that virtual space in your head. Your code and data is laid out. Binary is created that way. Your binary. So let me show you. So example again. Going back to this code, then you have a while loop, so it never exits. Right? So if you go to Linux, so you can see virtual space layout. Your layout of this T2 program. Okay. So PS T2 task T2 your program. This program process ID 90 7.1. Then there are a bunch of numbers, directories, where you can find 9071. So 9071, right? So here you have information. There is information about that process thread, right? Check out this maps, right? Map file. This is the layout of T2, that program, layout of that program on virtual space. So if you check out this T2, right? So huge numbers, right? This is huge numbers. So your actual, by looking at this, R means read, X means executable. X, right? That means your code instructions, right? Instructions are placed from this location to that location. Simple program, right? Super simple program. So you don't need much space, right? So this one is like 4K byte, right? 130. So 4K byte space, right? In virtual space, right? And then by looking at this, R read only, I think, read only data, okay, are placed from this location to that location. Right? And RW means read or writable. Sometimes you want to update data local variable, right? So that is located here. And in the heap, right? If you do dynamic memory allocation, what is dynamic memory allocation? If you in C language, right? If you call memory allocation, malloc, right? That is dynamic memory allocation. While we are executing your program, you want to allocate some memory area. In C, you use this keyword new. New is C++, sorry, C++, right? For dynamic memory allocation. That dynamically allocated memory are located in heap area. Heap. Okay. So heap is located from this very high, right? This place. Heap. Okay, this place. And the stack, right? So that is a library, right? Library are located here and stack. Stack, right? Stack is located somewhere here, right? So on this 248, right? 256 terabyte space, the half, right? Right below here, you have stack. This is a stack area. And your code is located here, read only data and read writable data, and heap. Heap is growing like this, and stack is growing like this. And virtual space. Okay, so the point is, each program is fully utilizing this virtual space. It is not precise, not 100%, but you can, for now, you can think. Your application program, each application program, okay, T1, T2, T3, each one is fully utilizing this virtual space. If you context switch, if you switch from task 1 to task 2, then task 2, right, T2 code will be placed here, read only data, read write data, heap is growing like this, stack is growing downwards. T3, you are switching out, then T3 is switched in, then virtual space layout, similar layout, right? Code, data, heap, stack, same virtual space layout. So each program is executed on this white. Nobody is using this white space but your application program. Then the rest, right? Physical memory. Physical memory is managed by operating system. Placing only requested page. If you are accessing that page, only that page will be placed here or somewhere. Main memory, right? Main memory. Some location. Okay. If that is empty. So next page could be located. First page could be located here in main memory, physical memory, and second page can be located here. The third 4K byte page can be located here. It is fully distributed. It is not placed in consecutive memory location. In virtual space, right? Code is located in consecutive memory locations. But actual code and data, actual code and data are distributed across this main memory. OS is operating system is doing that next. Okay, so we are going to repeat that explanation, and we will study with specific example later on. Not this week, I think. Next week we will play with specific example with Cortex A9. I have a real code, right? So things would be clear as we move on. So there is the motivation. Okay, let's read this. Now, Camden. Long time no see. What happened? Have you been here? Okay, one. Okay. Okay. So virtual memory again is a technique supported by operating system. Linux, Windows are providing virtual memory. Okay, virtual memory. So in short, virtual memory technique simply is using main memory, right? Using this main memory as a cache for hard disk. Because only requested page will be placed in main memory. Here, request page will be placed here. So if you take a snapshot of main memory, it is populated with pages from many different tasks. It looks very nasty if you are able to take a snapshot. Okay. Then the virtual space. So virtual memory is implemented with page. That means virtual space is divided, logically divided into fixed size block, 4K byte typically. Doesn't sometimes not only 4K byte. In Cortex A9, we have 4 different page sizes: 4K byte, 64K byte, 1 megabyte, 16 megabyte. 4 different page sizes. But typically, page size is 4K byte. So virtual space is logically divided into 4K byte pages. The same thing goes to main memory. Physical memory is also divided into 4K byte pages, right? Logically divided 4K byte, 4K byte. And requested page will be placed somewhere, some location. So load only requested page, into actual memory. Then operating system should create page table. That is important. Page table. Page table contains translation information, mapping information, but virtual address to physical address. That mapping information. Let me show you. So CPU is generating virtual address, right? And your program is executed on this virtual space. Then the first page in your program is located here in main memory. This animation. Example. Second virtual page is located here. The second, this green is main. Second physical page. The first physical page, second physical page, third, and so on. And third, 1, 2, 3, right? Third virtual page is actually located here. So it's mapping. So these arrows are showing mapping information. So then now context switch, right? 1 millisecond elapsed. Now it is time to execute new task P2. Then this virtual space, this whole virtual space is used by task 2. Okay, and then operating system is creating that mapping information. The first virtual page is not located in main memory. That is still in file disk. That means that page should be placed somewhere in main memory for execution. You have to have program code, right, and data should be placed in main memory. So CPU is able to access only main memory. Right? So that is mapping information. First page file disk, third page file disk, but fourth page is located here in main memory. That mapping information. So let's talk about page table. Page table. Then, so that is important information. Juan, okay, please. Okay. The thing is operating system, right? Operating system is executing your program. OS is executing T1, T2, T3. Right? So when OS executes T1, before executing T1, OS is creating page table. Right? So what is meant by page table? So I color coded it. Right? Page table is located in main memory. For each program, for task one, CPU OS is creating page table, and for task 2, operating system is creating separate page table. Task 3, OS is creating separate page table. Page table is composed of entries, right? Many different entries. We call that page table entry, PTE. Then how many entries you need for each program? So assuming, for simplicity, let's assume 32-bit computer system. 64-bit is 2-bit. Assuming 4K byte page. CPU generate 32-bit address, virtual address. This virtual space is divided into pages, 4K byte pages. Then how many pages you have in this virtual space? 4 gigabyte virtual space. So 4 gig divided by 4K. And how many pages you have? 2 to the power 1 million. 2 to the power of 20. So 10, 24 square. That many entries you need. That many virtual pages you have, right? That means you need to have translation information. First page is located somewhere, right? So first virtual page. This one is we can call virtual page number 0, virtual page number 1 and 2, and so on. Virtual page. Okay. So virtual page number 1 million minus 1. The million is this one. Okay. So then you need translation information. Right? What translation? You have actual physical memory, main memory. Main memory is also divided into bit size 4K byte block. So that is placed, okay, that is located here. Physical page number, let me cook up just 1,000. Second virtual page is located here. This one, physical page number 3. So that mapping information should be created. Okay? And then there is a page table. Page table contains that information. The first entry contains that information. Okay? This one, 1 and 2. First PTE contains that 1 information. Second entry contains 2 information, the translation information, and so on. That means you need 1 million entries. 1 million is 1024 square. You need that page table. And that page table is created by OS nodes, right? Because OS is doing that management, right? Placing that page into the main memory. OS is doing that data transfer. So OS knows, right? OS knows. Then mapping information. Then that page table itself is located somewhere in main memory. So let me use this one. So that is page table. Page table is located in main memory. Page table for T1, that is T1. And let's say page table for T2, and somewhere T3 and so on. So every time you do context switch, then you have to use new page table. And also CPU need to know the location of the page table. Okay. So now page table is located here to execute task 1. Then context switch it. Then page table is located from the location. How do you know that base location, start location of page table? Inside the CPU, inside the processor, you have a very special register. In case of ARM, okay, we have a system register called TTBR. The name is very intuitive. Translation table. That is translation table. Translation table base location. This is a base location. So that should be programmed to indicate the start location of the page table. So OS, every time context task switching happens, operating system is updating this TTBR register to point new location. Let's say page table for T3. So like this. Then OS knows, okay, I'm using that page table. CPU knows, okay, page table is located here because that register got changed. So Intel has a register, x86, how about x86? Intel has a system register, similar register called control register 3. That's Intel, x86. So CR3 register should be changed every time you do context switch, because that is pointing the location of a page table. So every CPU is providing that kind of system register. RISC-V, we studied last time, it is providing SATP register. The system address translation, some protection register. But the function is similar, right? You have to update SATP register because that register is pointing the location, the base location, page table. Okay. So the point is, page table is created by operating system that is placed in main memory. That is in main memory, right? So I color code it, right? So we have a page table. Green is main memory. Page table, and that is for loading code and data. So then how page table is accessed? Right? How page table accessed based on this virtual address. Here let's say virtual address, a 32-bit virtual address. 32-bit virtual address, and then we are using 4K by page. Then you can divide this virtual address into two parts: last 12-bit and the upper 20-bit. Because 2 to the power of 12, that is 4 K. So this one is called offset, page offset. So then upper 20-bit is selecting which page you are accessing. You are accessing this virtual page number 0, 1, 2, which page you are accessing. Okay? Because each one is 4K byte. And the last 12-bit is pinpointing within this page, which location you are talking about, which exact location you are talking about. That is the offset. Right? So the point is, using upper 20-bit, you are selecting virtual page number, which virtual page you are accessing. Simply address, right? So the page table is accessed with virtual page number like this. Okay. Page table register. We are talking about this TTBR, CR3, or SATP register. Okay. So page table register is pointing the start location. Okay. Start location of page table, and you have 1 million entries. In this here, I didn't specify ... but 1 million entries. 1 million entries. Then 20, right? 20 with 1 million entries, right? 1 million different pages. This 20 means 1 million different locations, right? So you can use this virtual page number as an index, like this. Index, right? Offset the virtual page number to index the PTE. So you are selecting particular PTE. That PTE, page table entry, contains translation information. Translation, virtual page to physical page. Right? You are talking about, for example, virtual address 1000. Then you are talking about 1, right? The last 12 bit, or 00012 bit. So 1 means you are talking about virtual page number 1. You are accessing VP1, right? Then you need to check out. You need to access second entry in PTE. Second entry, second 1. Everything is 0, but no. So 1 means you are accessing 0 and 1. Second entry in page table. That entry contains translation information, giving you physical page number. Main memory, right? So you have some physical page number. Let's say 2000. So then physical page number 2000. Then physical address should be 2000. Then add 3 more. Right? 2000. Then 3 more. That is physical page number. Then offset. So physical address. That physical address will be generated to access that specific page. That is mapped to. So I think this one then that is containing second entry contains that information. 2000. Second entry. So the thing is very simple actually. Physical each PTE has what? Has. Let me make it big. Page table. Page table. It contains physical page number. Simply. Physical page number. So using virtual page number, you are accessing particular entry. That entry contains physical page number. Because the thing you need to know is that page, virtual page is mapped to that information. Then mapping information is needed, right? Then mapping. Virtual page is actually located here. Then mapping information. That is what you need to know. Right? So that number, physical page number. But you know virtual page number by looking at virtual address. That virtual address is mapped to where? The physical page number. That is contained in this PTE. I know it is very confusing. We are going to repeat, okay, again and again for 2 weeks. So things will be clear. But take a look at this PowerPoint, and because we need to move a little bit fast. We have 3 weeks left, and we need to finish 2 important topics: virtual memory and security feature, trust zone. So we don't have enough time. So I'm going to push a little bit hard, move a little bit fast. So try to read that PowerPoint. Okay, any question before closing up? Okay, that's it. See you next time.
엑스트라 과제에 대해서 아까 질문드렸는데요. 이게 굉장히 짧은 시간에서 스위치하는 URP에서 프로세스 트리에드 메시지가 좀 붙여서 틀어져 이제 조사입니다.
정상이죠. 수밖에 없죠. 왜냐면 UART가 느리기 때문에. UART가 느리기 때문에 1ms면 중간에 끊길 수도 있잖아요.
어쨌든 좀 길게 하니까 안 끊기더라고요.
그렇지. 그럴 수도 있고. 길게 해도 끊길 수도 있고. 메시지가 나오는 중간에 딱 스탑이 되면 끊기는 거죠.
카운터만 제대로 올라가면 몇 번째 출력됐다 그것만 제대로 볼 수 있으면 되는 거죠.
그렇지. 그런 식이죠.
선생님, 다음에는 좀 페이지 테이블에서 이제 아까 CPU가 이제 디스크 스토리지는 이제 못 읽는다고 하셨잖아요.
그렇지. 그러니까 우리 CPU가 직접적으로 액세스하는 거 그런 걸 얘기하는 거지.
예.
그러니까 CPU가 ARM 프로세서라고 하면
네.
얘가 직접적으로 액세스하는 거. 직접적으로. 그러니까 얘는 어드레스를 통해서 피지컬 어드레스를 통해서 얘를 직접적으로 액세스할 수 있고 하드디스크는 우리가 I/O 장치라고 불리고 해요. 그렇기 때문에
그러면 디스크 스토리지를 이제 페이지 테이블에는 어떻게 등록돼요?
디스크 스페이스?
그러니까 스토리가 페이지 테이블이 이제 이렇게 연결되어 있잖아요. 정확히
아니 연결됐다는 게 아니라
예.
페이지 테이블에 있는 정보를 얘기하는 거죠. 이 정보가 뭘 나타내냐면
예.
첫 번째 요 페이지는 하드디스크에 있고 아직 메모리에 로딩이 안 됐다는 걸 의미하는 거지.
그냥 안 쓰고 있다는 그런 뜻입니다.
아니 모든 게 하드디스크에 있잖아.
예.
컴퓨터에 우리 프로그램이 전부 하드디스크 있잖아.
네.
근데 실행을 하려면 메인 메모리로 갖고 와야 돼.
예.
그런데 아직 메모리로 갖고 오지 않은 상태랍니다. 이렇게. 지금 이 페이지는 현재 하드디스크에 있고 메인 메모리에 로딩이 안 돼 있다는 거예요. 그러니까 얘네들은 근데 돼 있죠. 지금 요거를 보면 1이라고 써 있는 거.
예.
얘네들은 밸리드하다는 거거든. 밸리드하다는 건 뭐냐면 그 페이지들은 메인 메모리에 로딩이 돼 있다는 거예요. 여기 로딩이 돼 있으니까 CPU가 바로 이제 액세스를 할 수 있다는 거예요. 하드디스크에 있으면 CPU가 액세스를 바로 직접적으로 할 수 있는 게 아니고 일단 로딩을 시켜야 돼요. 그럼 이렇게
제가 그 궁금한 게 두 가지가 있어서 근데요. 그래서 제가 좀 이해를 잘 못해가지고 이제 레지스터가 두 부분으로 나뉘잖아요. 버추얼 페이지 넘버랑 offset.
아니 레지스터가 아니라 이건 어드레스.
네.
CPU가 만드는 이번에는 어드레스를 두 부분으로
네, 어드레스 두 부분으로 나누는데 그러면 이제 버추얼 페이지 넘버 같은 경우에는 그 페이지 테이블에서의 이제 그 인덱스를 하는 것이고 그다음에 저 offset 같은 경우에는 버추얼 스페이스의 위치를 의미하는 겁니다.
둘 다지 그러니까 현재 페이지가 선택이 되면 이게 지금 전부 4kB잖아.
네.
4kB고 그다음에 해당하는 버추얼 페이지. 그다음 해당하는 페이지가 지금 여기에 들어가 있다.
네.
이것도 4kB. 지금 요게 이 페이지가 여기에 웹이 돼 있다라고 하면 옵셋은 요 페이지에서의 정확한 위치를 내요. 위치를 내요. 이 페이지 내에서의 정확한 위치. 4kb니까. 버추얼 페이지 넘버로는 이 페이지 현재 페이지만 선택을 하는 거예요. 어드레스를 생각을 해보세요. 어드레스가 뭐야? 어드레스가 그 정확한 위치를 나타내는 거잖아요. 근데 그 위치를 나타낼 때 이걸 두 개로 분리를 해보면 두 개로 분리를 해보면 전체가 그냥 어드레스긴 한데 저 위에 20비트는 페이지 번호, 그다음 아래 12비트는 그 페이지가 선택이 됐을 때고
네.
그 여기서의 정확한 위치, 4km 정확한 위치를 내요.
네, 알겠습니다.
그러니까 실제로는 이 피지컬 페이지의 정확한 위치를 나타내는 거죠. 그러니까 어드레스 트랜슬레이션 할 때 이게 버추얼 페이지 넘버고 이게 최종적으로는 어드레스고 피지컬 어드레스로 갈 때 페이지 테이블을 참조해서 피지컬 페이지 넘버가 여기 들어갈 거고 옵셋은 그대로 옵셋은 변화 없어. 이건 그대로 그냥 카피. 이거 그대로 그냥 컨캐터네이션을 하면 이게 이제 이 어드레스가
그러면 이제 그 메인 메모리 같은 경우에는 그 연속적이지 않게 이제 위치한다고 하셨잖아요. 프로그램 코드가. 그러면 하드디스크, 그러니까 디스크 스페이스에서는 연속적으로 위치를 하죠.
우리가 컴파일 코드를 하면 C 프로그램 컴파일을 하면 그러면 내가 연속적인 위치에 바이너리가 연속적인 위치입니다. 버추얼 메모리 상에 버추얼 메모리 상하고 컴파일이 되기 때문에 연속적인 위치에 코드와 데이터가 있고 하드디스크요.
그럼 이제 디스크 스페이스랑 버추얼 스페이스에 이제 연속적으로 위치하는데 이제 메인 메모리에 위치할 때는 이제 좀 유동적으로.
그렇지. 어디에 여기 있는 페이지들이 어디에 위치해서 상관없어요.
네, 감사합니다. 아재 할 때 그려
이걸
그리고 저희 과제 할 때 바이너리가 만들어지는데 데이터가 있잖아요. 여기 데이터 위치하고 코드가 위치하는 건데 제가 매크로 과제를 할 때 느낀 코드에서 이제 메모리 액세스를 해서 데이터를 불러오는 부분이 킬로바이트가 떨어져 있으면 에러가 나서 신고음이 너무 멀다 이런 에러가 나서 파일 액세스인데
아닐 거야. 아니지. 지금 암을 우리가 사용하고 있잖아. 시험에 4kg 이상.
네, 그러니까 1024줄 이상 떨어져 있어요. 심볼 테이블이 너무 멀다면 더.
있습니까?
네,
예를 들어서 뭐 LDR
네, LDR을 넣으면
얼마 여기다가 2048 뭐 이렇게 하는 거.
저는 그냥 여기다가 이제 심볼을 넣어서 LDR 이걸 이런 에러가.
그러니까 지금 이거는 이제 인스트럭션의 인코딩 스페이스를 봐야 돼. LDR 인스트럭션이 머신 코드를 바뀔 텐데. 근데 이제 요 위치, 요 레이블이 위치한 위치를 이런 식으로 어쨌든 컴파일러가 숫자를 바꿔야 될 거예요.
네.
바꿔서 머신 코드에 집어넣어야 될 텐데 만약에 머신 코드 할당된 게 얘를 위해서 할당된 게 충분하지 않다면 그 머신 코드 관점에서 접근을 해야 돼요. 너무 많이 떨어져 있으니까 이 인스트럭션에 들어가지 않는다. 뭐 그런 거 같아요. 근데 LDR 뭐 이렇게 쓰면 되지 않나 근데? 하는 걸로 바뀌어.
그래서 저희 프로 여기다가 추가를 해줬었어요. 심볼 테이블을 가져오면서 추가해 주니까.
자, 그럼 같이 볼까요?